All right. In this video, we are going to be talking about continuity, more on continuity, and differentiable functions. So a function is differentiable when its derivative exists. Now, its derivative exists, we could use the definition of the derivative to look at the limits from the left side and the limit from the right side. If those limits exist and they're the same, then the function is differentiable. If the function is differentiable, then the function is continuous. The converse is not necessarily true. So if the function is continuous, it may or may not be differentiable. So like here, these three graphs are not differentiable at x is equal to 1. And here's why. If I were to look at x is equal to 1 right here, notice how my derivative of the left side, aka my slope of the left side, is -1. And my slope on the right side is +1. Because my slopes don't match, this tells me that the function is not differentiable at 1. Even though we could see that this absolute function is continuous, that's great, but it's not going to be differentiable at 1. So here, it tells us that, show that the absolute value of x minus 1 plus 2 is not differentiable at x is equal to 1. And like I said, if I were to put this more formally, the limit as x approaches 1 from the left of f of x is -1. And the limit as x approaches 1 from the right is +1. And since they don't match up, sorry, let me rephrase that. The limit, it's not the limit of the function, but it's the limit of the derivative. So it's going to be f of x minus, in this case, 2, then x minus 1 is equal to -1. And then the limit as x approaches 1 from the right of my limit definition of the derivative, f of x minus 2, x minus 1 is equal to 1. And since they don't match up, since limit does not equal limit f of x is not differentiable at x is equal to 1. All right. There's a video on number 9 that I've already posted on YouTube, so I'm going to skip number 9, but I am going to do number 10 here. 10 says, for what values of x is f differentiable? So if f is differentiable, then it has to be continuous. So here I'm going to be looking at two main points. I'm going to be looking at x is equal to 0, and I'm going to be looking at x is equal to 2. So if f is differentiable, then f is continuous. So I'm going to look at continuity at 0, and I'm going to look at continuity at 2. So at x is equal to 0, I have the limit as x approaches 0 from the right of f of x. And that's going to be the same thing as 2x, which is 0. And then I have the limit as x approaches 0 from the left, which is going to be, it's not left, to the right. That's going to be 2x minus x squared. And if I plug that in and substitute, that's going to give me 0. So I know that our function is continuous at 0. So that's a good thing for now. At x is equal to 2, I'm going to do the same thing. So the limit as x approaches 2 from the left of f of x, that is going to be 2x minus x squared. And if I were to plug in 2, that's going to give me 4, and then 4, that's going to be 0. And then I'm going to do the same thing here. From the right side, it's going to be 2 minus x, which is 0. So far so good. We know that f is continuous everywhere from negative infinity to infinity for f of x. Now we just got to see if it's differentiable at 0 and at 2. Now, remember that if it's differentiable, then that means that the derivatives are the same from the left side and from the right side. So now I'm just going to take the derivative of this right here. All right, so if I were to take the derivative, I'm going to get 2. I'm going to get 2 minus 2x, and then I'm going to get negative 1. And that's my derivative of f of x. All right, my main goal now is to figure out if my derivatives are the same at 0 and at 2. So now I have the limit as x approaches 0 from the left of my derivative function, 0 from the right of my derivative function. Oh, wait, that's just, yeah, let me do this again. 0 from the left, and then that is just 2. So that's just going to be 2. 0 from the right is going to give me 2 minus 2x. And if I were to plug in 0, I'm going to get 2. Since they match up, I have 2 here and 2 here. This tells me that I'm definitely differentiable at 0. So now I got to look at x is equal to 2 and do the same thing and see if it's differentiable everywhere or it's differentiable everywhere except at x is equal to 2. So I have the limit as x approaches 2 from the left of my derivative, and that right there is going to be 2 minus 2x. If I were to plug in 2 from the left, that's going to give me negative 2. Right, and then if I were to do 2 from the right, you'll probably notice that it doesn't match up because guess what? It's negative 1. I know. Since they don't match up, this tells me that f is differentiable everywhere except at 2. So to write this, I could say that f of x is differentiable from negative infinity to 2, and then 2 to infinity. Now, to fact check this, what you can do is plot this on Desmos just so that you know that, hey, we have the same slope here, but we don't have the same slope here, even though the function is continuous. All right. What we're going to do now is use the definition of the derivative and our derivative rules to evaluate the following. Now, remember that we had two definitions of the derivative. We had the difference quotient, and then we had the derivative at a point. So we got to figure out which one is what. Now notice how for this one, number 11, this one is the difference quotient because I have the limit as h approaching 0. So what I'm going to do here is think about, okay, the difference quotient had x plus h. So anytime I see x plus some number, I am going to go ahead and replace that with a regular x. So here, because I have h plus 1 and h plus 1, I am going to replace that with an x. And that's it. Now, I'm going to ignore the 9 for now because remember that if I were to think about the difference quotient, I have f of x plus h minus f of x over h. F of x is going to be your value at that particular point. So here, I'm trying to figure out what my x value is. So here, This is saying, looking at this right here, since I have h plus 1, this one here represents the value that I'm going to be finding in terms of my derivative. So this is saying I need to find the derivative at x is equal to 1. Which means if I were to plug in this right here, f of x, aka this is f of 1, and I plug this into here, I should probably get 9. Which is true because if I have 1 cubed plus 8 over 1, I get 9. So that's a good way for us to think about if my function that we found is correct or not. So we have our function, that's great, but we haven't found the derivative yet because I want the derivative at x is equal to 1. So I am going to find the derivative using my good old power rule. So I have 3x squared here. I'm going to rewrite 8 over the square root of x to be 8x to the negative 1/2, so that I get minus 4x to the negative 3/2. And then I'm going to plug in 1. And then, of course, if I simplify that, 3 minus 4 is just going to be negative 1. All right, part C. Part C is the same thing. So here, I'm using the difference quotient. So the limit as h approaches 0 of f of x plus h minus f of x over h. Anytime I see an x plus h or something plus h, I'm going to replace it with x. So here, I have f of x being cosine of x. Notice how here my x value that I'm trying to find out is 7 pi over 6. So this is saying find the derivative of cosine at 7 pi over 6. And we could also verify that if I were to do cosine of 7 pi over 6, I'm going to get root 3 over 2, which works. So now I'm going to take the derivative of cosine. That's just going to be negative sine. And then I am going to take the derivative at 7 pi over 6. So now I have negative sine 7 pi over 6. And to simplify that, that's just going to be 1/2. All right. Now, parts B and D, we're using the limit definition from above. This one right here. The alternate form of the definition of the derivative. So here, notice how we are approaching C. So in this case, this is saying, what is my derivative at x is equal to 4 for this function right here? And what is my derivative at x is equal to 1 for this derivative here? Remember that this 130 and this this 7 right here represents f of c, where your c value is going to be 4 or 1. Of course, you can obviously check that you'll get 130 and you'll get 7 if you were to plug in 1 here or 4 here. But this one's a little bit easier because they already gave you the function. All you have to do is just take the derivative of it. About 6x squared. And then this right here, 4x to the negative 1/2. Negative 2x to the negative 3/2. And then we're just trying to find the derivative at 4. And there's your answer. Obviously, you keep it like that. I don't want to simplify that, so just keep it like that and call it a day. Same thing here. We have 4x to the third plus 3x to the negative 1/2. Take the derivative. That's going to be 12x squared minus 3 over 2x to the negative 3 over 2. And then I'm just going to plug in 1. And call it a day. So that's just going to be 12 minus 3/2. And if I simplify that, that's going to be 10.5. All right, two more. Number 12. Remember that whenever we sketch something and we get a horizontal tangent line, that means that our derivative is 0. So what we're going to be doing here is finding the points on the graph of f of x where our tangent line is going to be horizontal. So in order to do that, we're just going to take the derivative. So 6x squared plus 6x minus 12, and we're going to set that equal to 0. I am going to simplify that, and I'm going to factor that. Let's see, that's plus 2 minus 1. So I get x is equal to 2, negative 2, and x is equal to 1. All right, so we have an x value of negative 2, and we have an x value of positive 1, and we're trying to find the points on the graph of f of x. So what you're going to do with negative 2 and positive 1 is not plug it back in into the derivative, but you're going to plug it back in into the function. So you're going to plug in negative 2 into f of x, and you're going to plug in 1 into f of x and see what you get. In this case, you are going to get 21 and negative 6. All right, number 13. Number 13 is going to be a lot of fun because this is essentially a preview of what you'll be doing later on. Number 13 has a name, but I'm not going to tell you the name until we hit that topic. So for 13, it says find if it exists a value c in the interval 1 to 4 such that the instantaneous rate of change of f of x is equal to 6 over the square root of x at c is the same as the average rate of change of f over the interval 1 to 4. Interesting. So first, what I'm going to do is think, okay, if I have the instantaneous rate of change at c, so this is saying for some c, that is going to be equal to the average rate of change of f over the interval 1 to 4. So that's saying this right here. All right, so what we need to do is figure out what my derivative is and figure out what f of 4 and f of 1 is. So I'm going to figure out what f of 4 is. That is 6 over 2, so that's 3. If I do f of 1, that's going to be 6. 4 minus 1, so negative 3 over 3 is negative 1. So now this is saying, when is my derivative going to be equal to negative 1? Okay, so now I just got to find out the derivative. So I have 6x to the negative 1/2. If I take the derivative of that, I'm going to get negative 3x to the negative 3/2. In this case, since I'm using c, I'm going to have negative 3 c to the negative 3/2. That's equal to negative 1. I'm solving for c, so I am going to go ahead and divide by negative 3. And that's going to give me c to the 3/2 is equal to 1/3. And then to solve for c, I'm just going to raise each power by the reciprocal. In this case, my reciprocal is going to be 2/3. So I'm going to raise it by the 2/3. That's going to give me an answer of 1 to the 3 to the 2/3. So that means that my c value is this lovely thing right here. All right, so what we're going to do is actually go back and plug this in to see that it actually works. So this is saying if I have f prime of 1 over 3 to the 2/3, this right here should give me negative 1 because that was my average rate of change. I'm going to rewrite that so that it's 3 to negative 2/3. You You'll notice that I have negative 2/3 and 3/2. If I do power to a power, that's just going to give me -1. So now I have -3, 3 to the -1. We know that 3 to the -1 is the same thing as 1/3. So now I have -3 times 1/3. That's the same thing as -1. So that verifies my C value being 1 over 3 to the 2/3. Very good problem. I really like that one. Just because you don't know the name of it, but we'll see in a couple of units. All right, in the next video, we will talk about interpreting derivatives. That one should be short since there's only 2 problems.